In this set of notes, we're going to use Tanabe Sugano diagrams to calculate the field strength of metal complexes. That means delta O, or maybe delta T for tetrahedral complexes. So it's a graphical method, but we're going to use tables of data to do it. We'll see two examples in here, and there's some more exercises you can work and post it online. Okay, we're going to start by looking at a D3 electron configuration up here at the top. And when you first start looking at one of these diagrams, you want to pay attention to what electronic transitions are possible. And you start by looking at this ground state. Okay, and these are color-coded. It's very difficult to tell in this diagram, but the top marked state here is a quartet A2G, and that's what this bottom line represents. And so what that means is that any transition that is allowed from that ground state must go to another allowed state. This is at least the selection rules that we talked about. So that means that we need to maintain that quartet configuration. And so this thing doesn't have the proper superscripts here, but that's a quartet T2G is our red line here. So that's what's up here, quartet T2G. And that's our first allowed transition, you can see, because there's never a line that is also a quartet that is between this ground state and that first excited state. So the next state that we see is this quartet T1G state in green, right? I'll label it here, quartet T1G. And then there's one more quartet, which is this blue line, quartet T1G, also way up here. Okay. These have the same label. This green line, these two right here, have the same name, but that's because this came originally from a P term and the other one came from an F term. Doesn't really matter now, but that they split out from different terms in our microstate table, right? So again, we have different allowed transitions. You see there's one allowed between that bottom, that ground state, that A2G and this T2G quartet, and then there's another that's to the green line, etc. There's to be a third one all the way up to this blue line. So these all represent optical transitions that are possible. We'll see these usually as UV or visible transitions. This first line to this quartet T2G, again, this red line right here would be the lowest energy transition. This would probably be in the visible range. The other ones might be in the UV range. All right, and in order to use the Tanabe Sugano diagram quantitatively, we need to have some values that we can read off of this. And so every time we use this method, we need to have two different transitions, which we just saw involve transitions from the ground state to these two first excited states. These would be the first two that we use for this diagram. And we're going to use, in our case, tables of data. There's different ways to do it, but this is very coarsely described right here as different values of delta O over B, which is this bottom axis. Okay, so we're looking at point 0. That's the first line right here, right? And then at 10, and then at 20, and then at 30. And this table actually goes out farther to 40 and 50, which isn't in our diagram. So if we look at the value, for example, at 10, the way we read this is the energy, this is this energy over B, units over here, is 0 all the way across because that's our ground state, right? So the quartet A2G, remember, is our ground state. The quartet T2G is our first excited state in red, right? And its value at 10.42 is 10.42. So if we were to read up here and read across, y equals x for that particular line, right? You'll see that that's true all the way down. Every time we have a value, 26, we see that copied over here, right? That just happens to be the case in this diagram. The next line that we have marked here is this quartet T1G, and again, at the value 10.42, if we read up, that this 17.09 right here indicates that that's the value at 10 roughly 10 in this x-axis. Okay. So to use this method, what we're going to need to use is a ratio of one energy over another, and we're going to find the best match on this curve, right? So we'll take our energy of our second transition divided by the energy of the first transition. We're going to get some ratio, and we're going to look for that ratio in this last column. And you see in this diagram, as we move from left to right across the diagram, these two lines are roughly parallel to each other, and so the ratio of this energy to this energy decreases as we go from a pretty large value right here to a pretty small value by the end, right? And you see that that's happening as you go down this, go across from left to right of this diagram, the ratio of energies decrease. That'll be our matching point here in a little bit. So this Raka parameter we've seen here, this letter B, appears in that Tanabe Sugano diagram in two places, and so we need to talk about what it is. So it's described as a measure of the inter-electron repulsion. Okay, so this is the repulsion between two electrons. That means that when a metal is really small and highly charged, the electrons are interacting very strongly, and this has a larger value. For us, we're not going to worry too much about what the number is, but you'll find that you'll see larger numbers for small ions like cobalt 3+, and you'd have a much smaller value if we were looking at ruthenium or something, a larger metal. So it does appear in both axes of the Tanabe Sugano diagram, and so we need to make sure that we deal with it. We have to solve it first in order to solve the other axis, essentially. So we need to use the Tanabe Sugano diagram to solve for the field strength. That's the whole purpose of this. So here are the steps for doing that. So step one, first of all, you need to take your wavelengths. Usually you're measuring this in a UV visible spectrum. So you need to convert them to energy, often in the form of inverse centimeters, right? Next, you need to calculate the ratio of transitions, meaning that you use the higher energy transition that you just solved and divide that by the lower energy one. This will give you a number greater than 1. And then you use that ratio in the Tanabe Sugano diagram like we talked about a second ago, and we'll demonstrate in a moment. But you find a match to that ratio of energies, and this would be between the second transition's energy and the first. Then you read to the left. For each of those values, you're going to have different E over B values, right? Different energy over that Raka parameter value. It's just a number right now, but we're going to use that to now calculate B because we know what E is, right? E is the energy that we calculated a bit ago up here, right? Converting the wavelength to energy. And then the only unknown then, since we know what E divided by B is, and we know what E is, we know what B is then. Okay, so you calculate B. We'll do that. And then you use that known Raka parameter now, reading down to the bottom of the diagram to calculate for the field strength, delta. Okay. So you know what delta over B is. That's the bottom axis. That allows us to solve. So we're starting with our first example now, which is a chromium ethylene diamine complex. So this is chromium, if you look at the formula, chromium 3+, which would be a D3 electron configuration. So we're using that same Tanabe Sugano diagram we looked at a moment ago. And you see it has 2 peaks in the UV visible spectrum, and that corresponds again to these 2 first transitions that are allowed, here and here. And so we're going to, first of all, convert those to inverse centimeters. We'll just tackle those one at a time, right? So our peak at 350 nanometers, we need to invert the length unit to get to inverse nanometers, and then convert using the appropriate conversion factor. It's basically a 10 to the 2 for the centimeters and a 10 to the 9 for the nanometers. It works out to be multiplied by 10 to the 7. This is a typical unit, around 28,000. It's usually in the tens of thousands of inverse centimeters for these optical transitions. All right, so we convert the lower wavelength, higher frequency, to get a higher energy transition, and then do the same for the 458 nanometer transition, giving us 21,000. Okay, 28,500 and 21,800 are the 2 values that we're about to use. Those again correspond to these 2 energies in this Tanabe Sugano diagram, but we don't yet know where we are in this x-axis. So the next step is to calculate the ratio. So the ratio is just the large number divided by the small number to give us a ratio here, 1.306. Okay. So now we find that in the Tanabe Sugano diagram, and this is extremely zoomed in with not enough significant figures shown, but 1.306 is somewhere in this range between 1.30 and 1.31. Just for the sake of this problem, we're going to use this line. Okay, I'm going to go ahead and highlight it here. These are going to be the different values we're about to use. So the next step is to calculate that Raka parameter B. Okay, so that uses these different values of E over B. And what we mean by that are these columns for the different transitions. So the first transition is to that quartet T2G, sort of this line, right? The second transition would be to that quartet T1G. Doesn't matter what their labels are again, but these are basically your E over B values, okay? And they apply to each of those two transitions. So if we look at our entry that we've highlighted here, 34.73 is the value for E over B for our first transition, okay? And we know that that ratio is basically the answer as we draw to the left at our appropriate, well, okay, so if we go back, this ratio here, 1.306, right, it represents the ratio of this top energy to the bottom energy. We found it. But by doing that, we're basically identifying the x-axis position and also the two y-axis positions. So this is our y-axis position for our first transition. What we know is E over B is equal to this number, and we also know that E, the energy itself, is the same as what we calculated a bit ago, right? That's just this answer for our lower energy transition, 1,830. So if you rearrange that to solve for B, B is equal to 21,800, the energy, divided by this ratio, 34.73. It's just a rearrangement of this little equation right here. So our answer we get is 628.6 inverse centimeters. That's our Rocca parameter. We can do the same for the other frequency, the other transition, using 45.40, right? So in this case, E over B is 45.4. We know the energy is 28,500, again, from what we calculated in the first step. So B, just by rearranging that equation and solving for B and plugging in that energy, right, we get 28,500 over 45.4 gives us basically the same number, right? I usually don't bother to do this twice because they're within error. I usually drop a significant figure at the end and call it good, okay? But you can check yourself to see if you have the right ratio or if everything else is checking out to make sure those Rocca parameters come out the same. But basically it must be true if you have the right ratio selected. So now that we know B, we only have one more piece to solve, and that uses this last column, delta over B, right? That's our x-axis position. That's reading down in our Tanabe Sugano diagram. So delta over B for our transitions is 34.73, right? So delta over B is 34.73. We just solved for B. Again, I sort of dropped that sig fig there to kind of represent that we don't know that much. And just to solve for delta, right? So delta is 34.73 times B, right? B is 628. We get this number. That's our answer. That's our octahedral field in this case. Okay. Delta in general, because we'll see at the end of all of this that this diagram can be applied to tetrahedral configurations as well. Okay. So it's the 5 steps. We'll do it again here in a second, but that's the process. All right, we're going to work one more problem here. In this case, it's a D6 metal complex, and the Tanabe Sugano diagram is more complicated because, of course, D6 can have, if it's octahedral, it can have two configurations here, T2G, and EG can be filled in this way, which would be high spin, right? Or they can be filled in a low spin configuration. And in between these two, there's a complete discontinuity because this has 4 unpaired electrons, right? While the lower diagram, that low spin configuration, has 0 unpaired electrons. Changes the multiplicity, right, in the ground state. So if we look at the this diagram, you see there's this big line dividing the two halves, and that is this discontinuity between high spin and low spin. You see it's very tiny here, but that's a pentet T2 state at the bottom. That's our ground state term. And for this particular configuration, there's only one excited state that is allowed with the same multiplicity. And it's this bold line, which if you follow the line way up here, it's a pentet E. Okay, pentet E. These are all Garada, but it doesn't matter. Okay, so a pentet E is the excited state. So we would see only one peak if this was a high spin D6 configuration. It's the only allowed transition, and maybe some super tiny shoulders that would represent some of these multiplicity, these transitions to other multiplicities. Those are so-called forbidden, right? But still possible. Okay, so after that line, after that bold line there, we have a new ground state. We have a new term, which is this singlet A. So now all of our excited states have to be singlets, right? And so that would be a transition with one of these electrons probably popping up to the EG or something like that, right? So the first singlet state we see that's excited is this singlet T. So I'll draw that in red, right? There's another one. This is T1, singlet T1, and there's a singlet T2G as well. Okay, so these are our first two excited states. There's others way up here. You see there's another one up here. These are all drawn in bold. So these are the transitions we're likely to see for this complex. And the first two peaks we'll see are always to this singlet T1 and singlet T2. And then if we look deeper in the UV, we would see other transitions as well. Okay, so this would be what we're going to call frequency 1 and frequency 2. Okay, so just like before, we're going to need to use some tables of data to do this quantitatively. If we look at this table, this is how we'll use this data, right? You'll always find this table with two different columns. So one for the high spin state with this pentet ground state and a pentet excited state, right? And that's these two lines right here. For the low spin configuration, you're going to find more than one column because we're going to have this excited T1G and excited T2G singlet states, right? One more time, those lines right there. Okay. You see that this happens, I think this got cut off here, but that's 10, that's 20, that's 30, that's 40, okay? So this discontinuity happens at around 18 in the x-axis, 18 units in delta over B, right? So somewhere between 15 and 20, we have that discontinuity. But you can see this little line here follows this pattern. It looks like it's y equals x. But in this column, you see there's no value here, which is equal to the value here. And so it tells us that we actually really do have to use the Tanabe Sugano diagram to solve for the octahedral field. There's no way just to do it by assuming that the transition is equal to that delta O. It is not in this case. So just like before, we're going to use these ratios to find basically an x-axis position somewhere, and then read across and use these energies to solve for B, the Rocca parameter, and then eventually just solve for delta O. The problem will work then is a cobalt complex. So this is a cobalt. If you look at the formula, it's cobalt 3+. And you'll see ethylene diamine is a reasonably strong field ligand, so we expect this to be low spin, especially for cobalt of all of the metals, right? So low spin D6 metal complex. We have two peaks also, and so in this Tanabe Sugano diagram, we just saw that if it was high spin, we would only expect to see one peak, and since we have two peaks, it's another piece of evidence that it's low spin. All right, so just like before, we need to turn those two peaks into energy units rather than wavelength units, and so we invert them, multiply them by 10 to the 6, so 21,550 is the lower energy transition going from 464 nanometers and converting 337 nanometers into these units gives us the 29,600. So just like before, we now take the ratio, the high value divided by the low value, and here we calculate 1.374. So we need to find that in our table, and we'll just find the closest value. We'll use 1.375 as that closest value. And now we have enough information to calculate B, right? Because these units in this table are in energy over B units, right? This is E1 over B, and this is E2 over B. So we'll just pick one of those. We get roughly the same answer if we solve it twice. And so we use E1 as our energy. That would be this frequency 1 here, 21,500. We know that E1 over B is this entry right here, 36.416. So rearrange that, solve for B, and we get 591.8 inverse centimeters. I encourage you to practice this sort of problem on your own here. All right, so that's Rocca parameter. The last step is to use that last column, delta over B, to solve for the octahedral field. So calculate the octahedral field. We know that delta over B is 39.44 or so. So rearrange that to solve for delta, and we have that ratio there, 39.44, multiplied by the Rocca parameter that we just calculated, and we get this. Okay, 23,300. It's a good, reasonable answer for a reasonably strong field ligand. Pretty large octahedral field for a first row transition metal.